Hi, I'm Alex. What if the strangest things in space aren't far off mysteries, but warning signs? Tonight, we explore real cosmic anomalies, signals with no source stars, behaving impossibly, and structures so large they challenge the foundations of cosmology itself. Nothing here is hypothetical. Every discovery is real, and everyone raises the same unsettling question: what are we missing? If journeys like this spark your curiosity, a gentle like and subscribe helps keep these stories alive. Let's begin October 19th, 2017. An object from outside our solar system came screaming through at 87,000 kilometers per hour. Nobody knew where it came from. Nobody knew what it was. And most importantly, nobody knew who or what sent it here. We had 11 days to find answers before it vanished forever into the cosmic darkness. Let me tell you why this discovery shook astronomy to its core. The Pan-STARRS telescope in Hawaii caught it first, just a moving point of light against the background stars. At first, astronomers thought it was ordinary, an asteroid maybe, perhaps a comet from the outer solar system, something doing its usual thing. But as they gathered more data, they realized this object was different, very different. It came from outside, from interstellar space. It had been traveling through the galaxy for who knows how long, and it just happened to pass through our solar system. They named it Oumuamua. It's Hawaiian, meaning scout, or messenger from afar. The name was chosen because the Pan-STARRS telescope is in Hawaii, but it turned out to be eerily appropriate. Here's what made it extraordinary: the shape. Based on how its brightness changed as it tumbled through space, astronomers calculated its dimensions: 400 meters long, 40 meters wide. That's a ratio of 10 to 1, like a giant cigar spinning end over end through the void. Think about that for a moment. No asteroid looks like that. No comet looks like that. Most space rocks are roughly spherical or irregularly shaped like potatoes tumbling through space. But Oumuamua, it was elongated, stretched out, almost artificial looking in its geometry. In all the asteroids and comets we've observed over decades, nothing has this shape. It's unique. But the strange shape was just the beginning. As Oumuamua approached the sun, astronomers watched it carefully. It passed inside Mercury's orbit. That's close, really close. The temperature on its surface would have reached hundreds of degrees Celsius. Here's what should have happened. When comets get that close to the sun, the heat causes their ice to vaporize. Gas and dust erupt from the surface, creating the characteristic tail that makes comets beautiful. It's what defines a comet. Oumuamua did none of that. No tail, no coma, no gas, no dust. Just a silent passage through the inner solar system. Complete silence. That was weird. If it wasn't a comet, maybe it was an asteroid, a solid rock with no volatile materials to evaporate. That would explain the lack of a tail. But then came the part that made no sense. After Oumuamua swung around the sun and headed back out toward interstellar space, astronomers tracking its trajectory noticed something impossible. It was accelerating. Not because of gravity. They'd calculated everything: the sun's gravity, the planet's gravity, everything. The math was precise. Oumuamua was moving faster than it should be. Something was pushing it. For comets, this is normal. It's called outgassing. When ice evaporates, it creates jets that act like tiny rocket engines, giving the comet extra thrust. But Oumuamua didn't have a visible tail. There was no obvious outgassing. So What was pushing it? Scientists proposed an explanation. Maybe Oumuamua was extremely thin if it was shaped like a pancake, or a sail just a few meters thick, but hundreds of meters across. Then radiation pressure from the sun could push it. Here's how that works. Photons from the sun carry momentum. When they hit an object, they transfer that momentum, creating a tiny force. For most objects, this force is negligible compared to gravity. But if an object is very thin and light relative to its surface area, radiation pressure becomes significant. The numbers worked. If Oumuamua was thin enough, sunlight could explain the acceleration. But here's the problem. Nobody wanted to say out loud. How does nature create something like that? How do you get a rigid structure, hundreds of meters across, but only a few meters thick? There's no known geological process that produces such objects naturally. This is where things got controversial. Abraham Loeb, chair of Harvard's astronomy department, published a paper suggesting we should consider another possibility. Maybe Oumuamua wasn't natural at all. It could be a probe sent by another civilization, Loeb said. It could be an artificial light sail. We should take this possibility seriously. The scientific community erupted. Most astronomers rejected the alien hypothesis outright. It's always the last resort in science. You only invoke extraterrestrials when you've exhausted every natural explanation. And many scientists thought Loeb was jumping to conclusions. But Loeb argued back. We couldn't explain Oumuamua with natural processes we know. The shape was wrong. The acceleration was wrong. Everything about it was anomalous. So why not consider artificial origins? The controversy raged for months. Some scientists thought Loeb was being reckless, damaging his reputation. Others admired his willingness to think unconventionally, to say what everyone else was thinking, but afraid to voice. Then in 2019, astronomers detected another interstellar object passing through our solar system. They called it Borisov. Borisov was completely normal. It had a tail. It had a coma. It outgassed. It behaved exactly like comets in our solar system. Chemical analysis showed it contained the same materials as our local comets. Borisov proved that interstellar objects can be ordinary, which made Oumuamua even more extraordinary by comparison. We now had two interstellar visitors. One was perfectly normal. The other was bizarre. Now here's something interesting about the timing that nobody talks about much. Pan-STARRS had only been operational for 7 months when it detected Oumuamua. 7 months. Before that telescope came online, we wouldn't have seen it. It would have passed through our solar system completely unnoticed. We wouldn't have known it was there. It's almost like Oumuamua chose to arrive exactly when we just developed the technology to detect it. Coincidence, probably, but it's a remarkable one. If Oumuamua really was a light sail, the engineering would be mind-boggling. To work as the calculations suggest it would need to be thinner than 1 millimeter per square meter of surface area, thinner than aluminum foil, thinner than paper, but it would need to remain intact after traveling through interstellar space for millions of years. Think about that. Micrometeorites constantly pepper any object in space. Cosmic radiation degrades materials. Interstellar dust, thin as it is, would sandblast anything over time. Yet, Oumuamua survived. There's no natural geological process we know of that can create such an object and have it remain intact for the journey. And here's another detail that bothers some astronomers. Oumuamua's trajectory through our solar system was lonely. It didn't pass particularly close to any planets. It came in, swung around the sun, and left. If you were designing a reconnaissance mission to avoid collisions while gathering data, this is exactly the path you'd choose. Safe, clean, observational. If it was a natural object ejected randomly from another star system, the probability of it following precisely this trajectory is less than 0.1%. The surface tells another story. Oumuamua was reddish in color, similar to objects in the Kuiper Belt at the edge of our solar system. This reddish coloring comes from cosmic radiation exposure over millions of years. The radiation essentially bakes the surface material, turning it red. But when scientists analyzed the reflection spectrum in detail, it didn't match any natural material we know. Not quite rock, not quite ice, not quite metal. Something else, something we couldn't identify. Here's where it gets even more interesting. Stephen Hawking and billionaire Yuri Milner have been developing something called the Breakthrough Starshot Project. The goal is ambitious: send a tiny spacecraft to Alpha Centauri, our nearest star system, using light sails powered by lasers from Earth. The technology they're developing is exactly what Oumuamua could be: a thin, lightweight sail pushed by radiation pressure. The resemblance is uncanny. Milner himself said it perfectly: either this is an extraordinary coincidence, or someone got there first. On January 2nd, 2018, the Spitzer Space Telescope captured the last faint image of Oumuamua. By then, it had passed beyond Saturn's orbit, still traveling at 26 kilometers per second, still heading out into interstellar space. It will take 20,000 years for Oumuamua to completely leave our solar system. After that, it will drift through the darkness between stars forever, alone, silent. Whatever secrets it carries are leaving with it. Think about this for a second. This object traveled through the galaxy for millions of years, since before our ancestors learned to walk upright on two legs. It passed through our solar system in 11 days. 11 days out of millions of years. And we almost missed it entirely. The astronomers named it Oumuamua, the scout from afar. But honestly, if this really was aliens, they have the worst driving skills in history. 87,000 kilometers per hour through the solar system. No turn signals, no braking. I wouldn't give them a license. And this is just the first story tonight. Trust me, what's coming is even stranger. Because at least with Oumuamua, we could see it. The next thing, we could only hear it. Once, for 72 seconds, and never again. But decades before, Oumuamua silently passed through, something else happened. Something reached out to us directly. Not a visitor drifting by. A call. Someone transmitted a signal straight at Earth. They chose the exact frequency that any intelligent civilization would recognize. They broadcast with enough power that an entire planetary civilization would need to generate. It lasted 72 seconds. Then complete silence, forever. Jerry Ammon didn't believe in aliens, not until the night of August 15th, 1977. He was working at the Big Ear Radio Telescope at Ohio State University. It was part of SETI, the search for extraterrestrial intelligence. Every day, the telescope scanned the sky, listening for radio signals that might indicate intelligent life somewhere out there. Most days the data was boring, just background noise from space, radio waves from natural sources, pulsars, quasars, the general hiss of the universe. Nothing unusual, nothing interesting. Amon's job was to review the printouts. The telescope recorded signal strength as numbers on continuous paper that fed out of a computer printer. Most of the time, those numbers stayed low. 1, 2, maybe 3. That was the baseline, the cosmic background. But on this particular night, reviewing data from a few days earlier, Amon saw something that made his heart stop, a sequence of numbers that climbed. 6, E, Q, U, J, 5. Let me explain. The system used numbers and letters to represent signal strength. 1 through 9 were numbers. Beyond that, letters took over. A meant 10, B meant 11, and so on. U was 30, the maximum on the scale. So this sequence meant the signal went from 6 up to 10, 15, 20, 30, peaked at 30, then dropped back down. A perfect bell curve of intensity. Amon grabbed a red pen. He circled the sequence. Next to it, he wrote one word. Wow. That's how it got its name. The wow signal. One astronomer's spontaneous reaction to seeing something impossible. Here's what made it extraordinary. The signal lasted 72 seconds. During that time, it was 30 times stronger than the background noise. 30 times. That's not a little blip. That's a powerful, focused transmission. The frequency was 1420 megahertz. That number should mean something to you. It's the hydrogen line, the natural frequency at which hydrogen atoms emit and absorb radio waves. Why does that matter? Because hydrogen is the most common element in the universe. It's everywhere. Every intelligent civilization would know about the hydrogen line. If you wanted to broadcast a signal that other civilizations might recognize, you'd choose this frequency. It's like choosing a universal emergency channel that everyone monitors. The signal was narrowband, extremely narrowband. It occupied one very specific frequency, not spread across a range. Natural radio sources like pulsars or stars emit across broad frequency ranges. They're noisy. They scatter their energy. But the wow signal, it was focused, precise, like the difference between random noise and a pure musical note. That narrowband characteristic is exactly what you'd expect from an artificial transmitter. The signal came from the direction of Sagittarius. That's toward the center of our galaxy, a region packed with stars. Here's another critical detail. Big Ear had 2 receivers that scanned the same patch of sky 3 minutes apart. The signal showed up on the first receiver, but not the second. That means the signal lasted less than 3 minutes. Probably the 72 seconds the data showed. Then it stopped. Just stopped. Amon was alone in the lab at midnight when he found it. He'd been reviewing hundreds of pages of boring printouts. Then suddenly this. His hands probably shook as he circled those characters. He checked the equipment. No malfunction. He checked the timestamps. Everything was correct. Then the realization hit him. I just caught something. Since 1977, astronomers have gone back to that same spot in the sky dozens of times. They've used more powerful telescopes. They've listened at the same frequency and nearby frequencies. They've searched for any sign of the signal returning. Nothing. The wow signal was a one-time event. Scientists have proposed several explanations. In 2016, a researcher named Antonio Paris suggested it might have been a comet. Two comets, actually 266P Christensen and P 2008 Y2. They were in that region of space at the time. Comets can emit radio waves when the solar wind interacts with their hydrogen clouds. But there's a problem with the comet theory. The signal was incredibly narrowband. Comets emit radio waves across a broad spectrum. The WOW signal's precision doesn't match what comets do. Others suggested it might have been interference from Earth, a satellite, an aircraft, some ground-based transmitter that happened to send a signal at just the right time. But Big Ear was designed to filter out terrestrial interference. The signal's direction didn't match any known satellite. At that time, there were no satellites in position to create what they saw. So what was it? Here's what makes it even more fascinating. To produce a signal that's strong from Sagittarius, about 220 light years away, you'd need a transmitter with at least 2.2 gigawatts of power. That's 2 nuclear reactors worth of energy, all focused into a single frequency. Only an advanced civilization could do that. Some scientists think it might have been a cosmic lighthouse. Imagine a lighthouse on the coast. It sweeps a beam of light in a circle. Ships only see a brief flash when the beam points at them. Maybe an alien civilization broadcasts a signal that sweeps across the galaxy. We just happened to be in the path when the beam swept past Earth. 72 seconds of contact. Then the beam moved on. If that's true, we might have to wait years, or even decades, for the beam to come around again. After the WOW signal, SETI launched a massive search. The SETI-A home project analyzed 5 petabytes of data. Millions of people participated using their home computers to help process the information. They searched for signals similar to the WOW signal. They found nothing. Absolutely nothing. Robert Dixon, the director of Big Ear, said something interesting. If I had to bet, I'd say it was a natural phenomenon we don't understand yet. But I can't rule out the other possibility, and that's what keeps me up at night. Why would an alien civilization only transmit once? Maybe they were testing their equipment. Maybe it was a one-time broadcast. Maybe they rotate through different frequencies, and we just caught them on the 1420 megahertz that one time. Maybe it was an accident, a signal spillover we weren't meant to receive. Or maybe it wasn't aliens at all. Maybe it was some rare natural phenomenon we've never seen before or since. The universe is full of processes we don't fully understand. The truth is, we may never know. The signal lasted 72 seconds in 1977 and never came back. It's a mystery, frozen in time. Imagine your phone rings at 3 in the morning. An unknown number. You miss the call. You call back. Nobody answers. No voicemail, no message, just silence. Forever. That's exactly what the WOW signal feels like. Some people ask, why would aliens only send one message? Well, maybe they have the same network coverage problems we do. Sorry, Earth signal's weak out here. Let me call you back in 50 years. At least with the WOW signal, it came and went. Quick, clean. But the next story, the star is playing hide and seek with us. It turns off, turns on, turns off, turns on. And every time it turns off, it goes dark. 22% of its brightness. Nothing, no planet, no comet, nothing can do that. Unless case 8462852. That's its official designation. But everyone calls it Tabby's star, and for the past 14 years, It's been doing something that not one star in 400 billion stars does. It disappears. Not once, multiple times, and nobody knows why. Let me tell you about this star. It's located 1,460 light years away in the constellation Cygnus the Swan. It's an A-type star, about 1.5 times the mass of our Sun and 6 times more luminous. Nothing about it looks special. From a distance, it's just another star, until the Kepler Space Telescope looked at it. Kepler was designed to find exoplanets by watching for tiny dips in starlight when planets pass in front of their stars. It monitored over 150,000 stars continuously. Most of them behaved exactly as expected. Tabby's star didn't. In 2011, its brightness dropped by 15%. Then it came back. In 2013, it dropped by 22%. Then it came back again. The dips were irregular. They didn't repeat at predictable intervals. They lasted different amounts of time. Sometimes the star would dim a little, sometimes a lot. 22% is enormous. Let me put that in perspective. When Earth passes in front of the Sun, from another star's perspective, the Sun's brightness would drop by 0.1%. Tiny, barely measurable. Jupiter, being much larger, would cause the Sun to dim by about 1%. 22%. That's not a planet. To block that much light, you'd need something massive, something as large as the star itself. Tabby's star wasn't discovered by professional astronomers alone. 200,000 people volunteered to help analyze Kepler data as part of a citizen science project. They flagged this star. Something's wrong here. Tabitha Boyajian, the lead scientist, checked it herself. She was stunned. The initial discovery set off a frenzy of theories. Someone suggested it might be an alien megastructure. The idea comes from a concept called a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson wondered what an advanced civilization would do if it needed enormous amounts of energy. Eventually, he reasoned they might build structures around their star to capture its energy output, not a solid shell. That would be impossible. But a swarm of energy-collecting satellites orbiting the star. If you were building something like that, it would block varying amounts of the star's light as the structure orbited. It would be irregular. It would dim the star by large amounts. It would look exactly like what we're seeing with Tabby's star. Most astronomers don't think it's an alien megastructure. The alien hypothesis is always the least likely explanation. But here's the thing, we had to consider it, because we couldn't explain the observations any other way. So, if it's not aliens, what is it? Scientists proposed a giant swarm of comets orbiting the star. If a family of comets passed in front of the star, they would block light irregularly. Their dust tails would create uneven dimming. But there are problems. Where did all these comets come from? You'd need an enormous number to block 22% of the star's light, and comet dust would make the star appear redder when it dims. Tabby's star doesn't do that. The color stays the same. Another theory suggested a recent collision. If two large objects smashed together near the star, the debris cloud could block light irregularly. But we'd expect to see excess infrared radiation from warm dust. We don't. In 2017, astronomers caught Tabby's star dimming again and observed it across multiple wavelengths. What they found was interesting. The dimming was more pronounced in blue light than in red light. That's consistent with dust. Small dust particles scatter blue light more effectively than red light. It's the same reason Earth's sky is blue. So maybe it is dust after all. But if it's dust, where's it coming from? Why is there so much? Why is the pattern so irregular? The current leading explanation is that Tabby's star has a large debris field around it, perhaps from a destroyed planet, perhaps from a massive collision, perhaps from some other catastrophic event. The debris blocks light irregularly as it orbits. But even this explanation isn't fully satisfying. Here's something that makes it even stranger. When astronomers analyzed old photographic plates from 1890 to 1989, they found that Tabby's star had dimmed by 20% over that century. This isn't a temporary phenomenon. This is a long-term process. After 2017, both amateur and professional astronomers began monitoring Tabby's star around the clock. They created the Tabby Alert Protocol. The moment the star starts dimming, observatories worldwide are notified immediately. Boyajian even launched a Kickstarter campaign to raise money for telescope time. Over 1,700 people contributed $100,000. That shows something important. This mystery captivates not just scientists, but the public too. Some people have proposed even more exotic ideas. Not a sphere, but a ring world. A massive ring rotating around the star. When it rotates, it blocks light in an irregular pattern. Mainstream science rejects this, but can't prove it wrong. Think about what would happen if our sun suddenly lost 22% of its brightness. Earth would get cold immediately. Global temperatures would drop about 8 degrees Celsius. Ice sheets would expand. We would panic. Here's a puzzling thing. If this really is a Dyson sphere under construction, why is there only one star like this? Out of 400 billion stars, just one. Either these structures are extremely rare, or we're looking at a very special moment in this star's history. Imagine you're the only person on Earth who has a weird habit of turning lights on and off in a strange pattern. And out of 8 billion people, we just happened to catch you doing it. That's the odds with Tabby's star. 1 in 400 billion. A friend asked me, why would aliens build a Dyson sphere there where we can see it? Well, maybe they didn't think we were smart enough to notice. Surprise, but if you think a blinking star is strange, wait until you hear about the explosion that shouldn't exist. In June 2018, telescopes around the world caught something. An explosion. 100 times brighter than a supernova, faster than anything we'd ever seen, and completely, absolutely should not exist. A 2018 cow. That's not some clever scientific acronym. It literally means cow. The automated naming system randomly assigned those 3 letters, and the name stuck. Because this explosion, it broke every rule about how a star can die. June 2018. Alarms went off simultaneously at 7 observatories around the world. Unknown transient, extreme luminosity. Astronomer Anna Ho at Caltech looked at her screen and thought, what the hell is that? It wasn't a galaxy 200 million light years away. At first, astronomers thought it was a normal supernova. Stars explode all the time. We detect dozens every year. It's part of the cosmic cycle. Stars are born. They live. They die. Sometimes violently. But as data came in, they realized AT 2018 cow was completely abnormal. Very abnormal. First, the brightness. Supernovae are already incredibly bright. They can outshine entire galaxies for brief periods. They're among the most energetic events in the universe. AT 2018 cow was 10 to 100 times brighter than a typical supernova, 10 to 100 times. That's not a little bit brighter. That's incomprehensibly, impossibly bright. Here's what that means in practical terms. AT 2018 Cow released energy equivalent to what our sun would emit over 100 million years in a few weeks. Think about that. 100 million years of solar output compressed into weeks. Where does that energy come from? How does it get concentrated like that? Then there was the speed. Normal supernovae take weeks to reach peak brightness. The explosion happens. Light starts spreading outward, and we see it gradually brighten over time. It's a slow build. AT 2018 Cow reached peak brightness in days, not weeks, days. Then it faded quickly. Most supernovae stay bright for months, gradually dimming. AT 2018 Cow blazed for a few weeks, then disappeared. It was like someone turned on a cosmic flashlight, shined it briefly, then switched it off. Fast, unnaturally fast. The temperature was extreme, tens of thousands of degrees Celsius. The light spectrum didn't match any known type of supernova. It was pumping out huge amounts of ultraviolet light and X-rays, and the debris was moving. Fast, really fast. When a normal supernova explodes, material flies outward at about 1% the speed of light. That's already incredibly fast. But AT 2018 Cow, its debris was moving at roughly 10% the speed of light. Nothing we knew about stellar death could explain this. As astronomers dug through archives and monitored the sky more carefully, they found more events like it. Not many, maybe 30 since 2018, but enough to realize AT 2018 Cow wasn't alone. These events formed a new class, fast blue optical transients, FBOTs. Fast. They peak and fade in days or weeks instead of months. Blue. They emit lots of ultraviolet light, indicating extreme temperatures. Optical. We can see them with regular telescopes, not just X-ray or radio instruments. Scientists proposed several theories about what causes FBOTs. Theory 1, the birth of a black hole or neutron star. When a massive star dies, its core collapses. If the core is heavy enough, it becomes a black hole. If it's lighter, it becomes a neutron star. Normally, the collapse releases energy that blows apart the star's outer layers. That's a standard supernova. But maybe in some cases, the energy gets released differently. Maybe it creates a jet that punches through the star's outer layers and shoots into space. This jet would create a bright, fast transient that looks different from normal supernovae. Theory 2, tidal disruption. A star wanders too close to a black hole. The black hole's gravity literally tears the star apart. The stellar material spirals into the black hole, heats up to extreme temperatures, and emits enormous amounts of energy. Tidal disruption events are known to happen. We've seen them, but most are slower than FBOTs. They take months to peak and fade. FBOTs are much faster. Maybe FBOTs are a special type of tidal disruption. Maybe a small black hole disrupts a white dwarf or neutron star instead of a normal star. The dynamics would be different, potentially explaining the speed and brightness. Theory 3, collisions between compact objects. A white dwarf slams into another white dwarf, or neutron stars collide. The collision releases enormous energy in an instant burst that could create an FBOT. As of 2025, we still don't know for certain. FBOTs are so new, just a few years of study. Each new detection gives us more data. We're narrowing down the possibilities, but we don't have a definitive answer yet. Here's what makes this significant. For centuries, we've studied supernovae, we developed detailed models of how different types work. We thought we understood exploding stars pretty well. Then AT 2018 Cow showed up and broke everything. It forced astronomers to realize there are types of cosmic explosions they hadn't anticipated, processes they didn't know about. There's another weird detail. AT 1218 Cow happened in a dwarf galaxy, a small galaxy with relatively few stars and low metallicity, not many heavy elements, conditions similar to the early universe. Do FBOTs only happen in extreme environments? Are they more common in the early universe when conditions were different? Some scientists think we're witnessing a baby black hole being born, not a slow, steady process, but an emergency delivery. Matter falling into a newly formed black hole extremely rapidly, releasing tremendous light. Here's something strange. With normal supernovae, we can often identify the progenitor star. We look at old images of that region and say, there, that star. That's the one that exploded. With AT 2018 Cow, no progenitor star in the old images. Either it was too dim to detect or there was no star. What explodes when there's no star? FBOTs are similar to gamma ray bursts, the most powerful explosions in the universe. But gamma ray bursts emit mostly gamma rays. FBOTs emit visible light. Maybe it's the same type of event, but the energy comes out in different directions. Since 2018, we've found about 30 FBOTs scattered across the universe. No clear pattern. They happen everywhere. They might even be multiple different types of events that just happen to look similar. Think about this: a star 200 million light years away did something in 2018, but it actually happened 200 million years ago when dinosaurs still ruled Earth. Its light traveled all that time to reach us, exactly when we had the technology to understand it. Partially anyway. The automated naming system didn't know it was naming a record-breaking explosion. If it had known, maybe it would have chosen OMG instead of cow. This impossible explosion, at least, has concrete characteristics. Bright, fast, hot, but the final story of Act 1. It's about a star that shouldn't exist, not because of what it does, but because it's there. This star is older than the universe. You read that right? Older than the universe, and we don't know how. HD 140283, the Methuselah star, named after the biblical figure who supposedly lived 969 years. But this star, it's been alive for 14 billion years. There's one small problem. The universe is only 13.8 billion years old. So, how the hell can a star be older than time itself? Let me explain why this is such a massive problem. The star is located 190 light years away in the constellation Libra. You can see it with binoculars if you know where to look. It's a subgiant star, meaning it's exhausted the hydrogen in its core and is starting to evolve off what we call the main sequence. Stars like this are ancient. They formed when the universe was young. Astronomers have several methods for estimating a star's age. Method 1. Chemical composition, specifically metallicity. The universe started with almost pure hydrogen and helium. That's it. No heavier elements. Over time, stars have created heavier elements through nuclear fusion. When massive stars explode as supernovae, they scatter these heavy elements, which astronomers call metals, into space. Future generations of stars form from gas enriched with these metals. So, a star with very few metals probably formed early, before many stellar generations had enriched the interstellar medium. The Methuselah star has extremely low metallicity. It contains about 250 times less iron than our Sun. That suggests it formed very early, when the universe was young and heavy elements were rare. Method 2. Nuclear fuel consumption. Stars fuse hydrogen into helium in their cores. When they run out of hydrogen, they start fusing helium into heavier elements. The rate of these reactions depends on the star's mass and composition. By observing a star's temperature, brightness, and composition, you can estimate how long it's been burning and therefore how old it is. When astronomers applied these methods to the Methuselah star, they got an uncomfortable result. The star's age came out to around 14 billion years. The error bars technically allow for ages slightly younger, around 7 to 13.8 billion years, but it's cutting it extremely close. Here's the problem. The universe itself is only about 13.8 billion years old. We know this from multiple independent measurements: the cosmic microwave background, the expansion rate of the universe, the ages of the oldest star clusters. They all point to an age of about 13.8 billion years. So, how can a star be 14 billion years old in a 13.8 billion year old universe? The math doesn't work. Initially, when this result came out, some people suggested maybe our measurement of the universe's age was wrong. Maybe the universe is older than we thought. But as measurements improved, the universe's age became more certain. It's definitely around 13.8 billion years, with very small error bars. So, the problem must be with the star's age estimate. But how could we be wrong? The methods for estimating stellar ages are well established. They're based on solid physics. The key is understanding what the error bars mean. The Methuselah star's age is around 14 billion years, with uncertainties that technically allow for it to be as young as 13.7 or 13.8 billion years. That's just barely younger than the universe. It's uncomfortable, but technically possible. If the star formed very soon, after the Big Bang within the first few 100 million years, it could be that old. But even this is problematic. The very first stars in the universe were different from stars today. They formed from pure hydrogen and helium with no heavy elements. These first-generation stars were probably very massive and short-lived. The Methuselah star doesn't fit the profile of a first-generation star. Second-generation stars formed from gas, enriched by the first supernovae. They would have small amounts of heavy elements. The Methuselah star has those small amounts, consistent with being second generation. But second generation stars wouldn't have formed immediately after the Big Bang. It would take time for the first stars to die and enrich the interstellar medium, maybe a few 100 million years. So, the Methuselah star probably formed at least a few 100 million years after the Big Bang. That would make its maximum possible age about 13.5 billion years or less. But the observations keep suggesting it's older than that. If the star really is 14 billion years old, it would have had to form just a few 100 million years after the Big Bang. But back then, the universe was still hot, flooded, with radiation lacking many heavy elements. Conditions were extremely different from today. There are many other old stars. Most have ages between 12 and 13 billion years. They're all younger than the Methuselah star. Why is this one star so much older than everything else? The Gaia satellite launched in 2013 has measured the distances to billions of stars with unprecedented precision. It's updated the Methuselah star's distance measurement several times in 2018 and 2020. Each update has slightly reduced the age estimate from about 14.5 billion years down to around 14.0 billion years. But it's still not enough. Some scientists have proposed exotic ideas. Maybe the earliest generation of stars could use dark matter as fuel. These hypothetical dark stars might live much longer than normal stars. Could the Methuselah star be a remnant dark star? It's an extremely speculative theory with no proof. If there really is a star older than the universe, does that mean our entire cosmological timeline is wrong? Or just our models of stellar evolution? Or is there something about the early universe we don't understand? The James Webb Space Telescope might help resolve this. It can observe the star in more detail, analyze its composition more precisely, and measure its distance more accurately. Maybe we'll have an answer in the next few years. Imagine you meet someone older than your grandparents. No problem. But if you met someone older than human history itself, that's what the Methuselah star feels like. Maybe this star is just lying about its age, like we do on social media. Oh, I'm not that old, it's just the light makes me look older. And that's 5 stories tonight. 5 things that shouldn't exist. An object from outside our solar system. A signal from the darkness. A star that blinks like a light switch. An explosion that breaks every rule. And a star older than time itself. But trust me, we're just getting started. Because Act 2, we're going to talk about things that aren't just strange. They're enormous. So big, they challenge everything we understand about how the universe is organized. Forget your concept of big. Forget galaxies. Forget galaxy clusters. I'm talking about structures spanning billions of light years. So large that according to theory, they're not allowed to exist. But they do, and they're challenging everything we know about the cosmos. 3.3 billion light years. That's the size of the giant arc, 3 times larger than the theoretical limit allows. And it's not alone. Let me put that in perspective. Light travels at 300,000 kilometers per second. In 1 year, it covers about 9.5 trillion kilometers. That's 1 light year. Now multiply that by 3.3 billion. That's how wide this structure is. It takes light 3.3 billion years to travel from one end to the other. The entire observable universe is only 93 billion light years across. The giant arc is a significant fraction of that. It's one of the largest structures ever discovered. In 2021, a PhD student named Alexia Lopez at the University of Central Lancashire was analyzing data from galaxy surveys. She was looking at how galaxies are distributed in space, and she noticed something that shouldn't be there: a curved arrangement of galaxy clusters, like a giant arc stretching across the sky. She measured it carefully, ran the statistics, checked her calculations again and again. The structure was 3.3 billion light years across. She was nervous about publishing. She knew what the reaction would be. Structures this large aren't supposed to exist. Then in 2024, her team found something else. Another enormous structure. They called it the Big Ring. This one was 1.3 billion light years in diameter. Not quite as large as the giant arc, but still massive. Still far beyond what theory predicts. Here's the kicker. Both structures are located about 9.2 billion light years from Earth, in the same region of the sky. That's suspicious. It suggests they might be related somehow. Maybe parts of an even larger structure we can't fully see yet. Now, why is this a problem? Let me explain something called the cosmological principle. This principle is fundamental to our understanding of the universe. It states that when you look at the universe on large enough scales, it should be roughly uniform, homogeneous. No matter which direction you look, you should see roughly the same density of matter. No huge structures, no massive voids, just smooth, even distribution. This principle is built into the standard model of cosmology. It's supported by observations of the cosmic microwave background, which shows that the early universe was remarkably uniform. The cosmological principle is why we can use the same laws of physics everywhere in the universe. But the giant arc and big ring challenge this principle. They're too large. According to calculations based on the standard model, structures shouldn't be able to grow larger than about 1.2 billion light years. That's the theoretical limit based on how gravity has had time to pull matter together since the Big Bang. The giant arc is nearly 3 times that limit. Even the big ring at 3 billion light years pushes right up against the boundary. These structures shouldn't exist. Some astronomers questioned whether they're real or just statistical flukes. When you look at the distribution of galaxies, you can sometimes see patterns that aren't really there. Your brain looks for connections. You might see a line or arc of galaxies that's just coincidence. But Lopez and her team did careful statistical analysis. The probability of the giant arc being a random arrangement is about 1 in 6,000. That's pretty low. The structure appears to be real. The big ring's statistics are even more compelling, and the fact that both structures are in the same region of space makes coincidence less likely. When Lopez first presented her findings, some senior astronomers were skeptical. A few even criticized her publicly. "You're seeing patterns in noise," they said. "These structures can't be real because theory says they can't exist." But Lopez stood by her work. The data was solid. The statistics were clear. Something enormous was out there, whether theory allowed it or not. So, what are they? One possibility is that they're related to something called baryon acoustic oscillations. In the early universe, sound waves traveled through hot plasma. These waves left an imprint on how matter is distributed today. They create a preferred scale for structures. But the giant arc and big ring don't match the expected size from baryon acoustic oscillations. They're much larger. Another possibility is that they're related to cosmic strings. These are hypothetical, one-dimensional defects in space-time predicted by some theories, but never observed. If cosmic strings exist, they could create large-scale structures as galaxies form preferentially along them. But cosmic strings are speculative. We have no direct evidence they exist. The most troubling possibility is that our cosmological model is incomplete. Maybe the cosmological principle isn't as robust as we thought. Maybe the universe has large-scale structure that we didn't account for. Maybe at the largest scales, things are more complex than our models predict. This wouldn't mean the Big Bang theory is wrong. It would mean we need to refine our understanding of how structure formed in the universe. We'd need to modify our models, add new physics, consider possibilities we haven't thought of yet. That's how science works. You make observations, build models. When observations don't match models, you update the models. As of 2025, the giant arc and big ring remain controversial. Some astronomers are convinced they're real structures that challenge fundamental principles. Others are more skeptical, thinking they might be statistical anomalies or misinterpretations of data. What's clear is that the universe at the largest scales is more complex than we thought. Whether these structures turn out to be real anomalies or something else, they're pushing us to think harder about how the cosmos is organized. If these structures are real, if they really do violate the theoretical size limit, then something is wrong with our understanding. Either gravity works differently at these scales, or there are processes we don't know about, or the universe is fundamentally lumpier than the cosmological principle suggests. It's like finding a building taller than Mount Everest. Theory says it's impossible. The materials can't support that height. Gravity won't allow it. But there it stands. Now you have to explain how. And if you think giant structures are strange, what about giant emptiness? What about a region of space that should contain 2,000 galaxies, but only has 330 million light years of emptiness? Like a giant bubble in the universe. Almost nothing there. Let me tell you about one of the strangest features of the cosmic landscape. It's called the Boötes Void, and it's one of the largest supervoids in the nearby universe. The void is enormous, 330 million light years across. To put that in perspective, that's more than 3,000 times the diameter of the Milky Way. It's a huge volume of space. Based on the average density of galaxies in the universe, this volume should contain about 2,000 galaxies. That's what we'd expect. That's what the math predicts. But when astronomers survey the Boötes Void, they find only about 60 galaxies. 60 out of 2,000. The rest is empty. Not completely empty, but remarkably void of matter compared to what should be there. The void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were mapping the distribution of galaxies and noticed this huge empty region in the constellation Boötes. Initially, they weren't sure if it was real. Maybe they'd missed some galaxies. Maybe their detection methods weren't working properly in that region. But follow-up observations confirmed it. The void is real. There really is a massive bubble of space with almost no galaxies in it. Now, voids aren't unusual in the universe. The cosmic web consists of filaments of galaxies surrounding voids. It's like soap bubbles. Matter collects on the surfaces where bubbles meet, leaving empty space inside. Most voids are tens of millions of light years across. They're common. But the Boötes Void is special. It's much larger than typical voids. It's one of the largest known supervoids in the observable universe, and its existence raises questions about how structure formed in the cosmos. Here's how voids form. The universe started out almost perfectly uniform. The cosmic microwave background shows us that at 380,000 years after the Big Bang, matter was spread almost evenly throughout space. There were tiny density variations, but incredibly small. Over time, gravity amplified these variations. Regions that were slightly denser attracted more matter and became even denser. These became galaxy clusters and filaments. Regions that were slightly less dense lost matter to their surroundings and became voids. Gravity carved the universe into the cosmic web we see today. Computer simulations of this process can reproduce the cosmic web. Filaments, clusters, and voids all emerge naturally from gravity acting on initial density variations. But the simulations also predict limits. Voids can only grow so large given the age of the universe and the strength of gravity. The Bode's void is close to this limit. It's about as large as voids can theoretically get. That makes it interesting because it's an extreme example. It's testing our understanding of structure formation. If our models are correct, we shouldn't see voids much larger than Bode's. If we do, it would suggest something is wrong with our models. So far, the Bode's void fits within theoretical limits, but it's close to the edge, and that makes it worth studying carefully. There's another interesting aspect. The few galaxies inside the void are weird. Some are forming stars at unusually high rates. Some have unusual shapes or characteristics. The isolation has affected them. Think about it. If you're a galaxy in a dense region of space, you're constantly interacting with other galaxies. You're pulling on them gravitationally. Sometimes you collide and merge. You're exchanging gas. You're part of a busy neighborhood. But if you're a galaxy in the Bode's void, you're alone. Your nearest neighbor might be millions of light years away. You're evolving in isolation without the gravitational harassment that galaxies in dense regions experience. This isolation might change how you evolve. Maybe you retain more gas because nobody is stripping it away. Maybe your star formation happens differently. Maybe you develop unusual characteristics. The galaxies in the Bode's void give us a chance to study what happens when galaxies are isolated. But the fundamental question remains, why is the Bode's void so empty? The answer probably goes back to the initial conditions of the universe. This region must have started out with slightly lower density than average. Over billions of years, gravity pulled matter out of the region toward denser areas, creating the void. But why was this region less dense to begin with? That's a deeper question related to whatever process created the initial density variations in the very early universe. Most cosmologists think these variations came from quantum fluctuations during inflation, a brief period of exponential expansion right after the Big Bang. These quantum fluctuations were random. Some regions ended up slightly denser, some slightly less dense. Most variations were small, but occasionally by chance, you'd get a larger variation. The Bode's void might be the result of one of these chance larger variations in the initial conditions. It's remarkable when you think about it. The emptiness we see today, 330 million light years across, originated as a tiny quantum fluctuation in the first fraction of a second after the Big Bang. That microscopic variation has been amplified over 13.8 billion years into this enormous supervoid. The universe is strange like that. The smallest things can have the largest consequences given enough time. It's like a scar from the universe's birth, stretched and grown over eons. Like living in the Sahara Desert, your nearest neighbor is hundreds of kilometers away. No shops, no restaurants, no other people. You'd develop differently. You'd adapt to the isolation. That's what happened to the galaxies in the Bode's void. But at least the void is real space. Empty, but real. The next story, it's about a cold spot in the background radiation of the universe. A spot that's too cold. The probability of it appearing randomly is 2%. We're living in one of the 50 universes that would have this. Or maybe something else created it. 2.725. Kelvin. That's the temperature of the universe, everywhere. Except one spot. That spot is 70 microkelvin colder, and nobody knows why. Let me tell you about one of the most puzzling features in cosmology. It's called the CMB cold spot, and it's been confusing scientists since 2003. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, when the universe was 380,000 years old. It cooled enough that electrons and protons could combine to form neutral hydrogen. Before this, the universe was opaque. Photons couldn't travel far before hitting free electrons. After this moment, the universe became transparent. Photons could travel freely. The CMB is made of these photons. They've been traveling through space for 13.8 billion years. We see them today as faint microwave radiation coming from all directions. The remarkable thing about the CMB is how uniform it is. If you measure its temperature in different directions, it's almost exactly the same everywhere. About 2.725 Kelvin, just a few degrees above absolute zero. But there are tiny variations. Some regions are slightly warmer, some slightly cooler. The temperature differences are about 1 part in 100,000. These variations are the imprints of density fluctuations in the early universe. Regions that were slightly denser were slightly cooler in the CMB. These dense regions eventually became galaxies and galaxy clusters. So the CMB is incredibly important. It's a snapshot of the universe when it was just 380,000 years old. By studying the pattern of hot and cold spots, we can learn about the initial conditions of the universe. Satellites like COBE map and Planck have mapped the CMB in exquisite detail. When scientists analyzed these maps, they found something unexpected. There's a region of the sky about 10 degrees across that's significantly cooler than expected. This is the CMB cold spot. It's not just a little cooler, it's about 70 millionths of a degree cooler than average. That might sound small, but in the context of the CMB's tiny variations, it's huge. The cold spot is located in the constellation Eridanus. It's oval-shaped, spanning about 10 degrees by 5 degrees. That's roughly 50 times the apparent size of the full moon. Based on our standard model of cosmology, we can calculate the probability of such a large, cold region appearing by chance. The probability is about 2%. Not impossible, but unlikely. 2% means that if you ran the universe 100 times with random initial conditions, you'd expect to see a cold spot like this in about 2 of those universes. We live in one universe, so either we're unlucky and happen to be in one of the 2%, or there's something special about the cold spot. Scientists have proposed several explanations. One idea is that the cold spot is caused by a supervoid, a huge region of space with fewer galaxies than average. If there's an enormous void between us and the CMB in this direction, photons passing through it lose energy due to something called the integrated Sachs-Wolf effect. Here's how it works. As photons enter a void, they climb out of a gravitational well, losing energy. As they leave the void, they fall into a gravitational well, gaining energy. If the universe weren't expanding, these effects would cancel out. But because the universe is expanding, the void gets larger and less dense, while photons are crossing it. This means photons gain less energy on the way out than they lost on the way in. Net result, the photons end up cooler. So a supervoid could create a cold spot in the CMB, and indeed, astronomers have found evidence of a large void in the direction of the cold spot. But even with this void, calculations suggest it can only account for a small part of the cold spot's coldness. You'd need an absolutely enormous void to explain the full effect. Another theory suggests the cold spot might be related to a collision between our universe and another universe in a multiverse scenario. In some versions of cosmic inflation theory, our universe is just one bubble in an infinite foam of universes. If another universe bubble collided with ours early on, it would leave a mark in the CMB, a circular region that's colder or warmer than average. The Planck satellite confirmed the cold spot in 2013 with even better data. It's definitely there. It's definitely anomalous. This is pretty exotic. There's no direct evidence for it beyond the cold spot itself, but it shows how puzzled scientists are. They're willing to consider multiverse collisions. If this is real, if our universe really did collide with another, it would be evidence that countless other universes exist. We'd be living in a multiverse. A third possibility is that the cold spot is just a statistical fluke. 2% probability means it's rare, but not impossible. Sometimes rare things happen. Maybe we just happen to live in a universe where this unlikely feature exists. The challenge is that we only have one CMB to observe. We can't run the experiment again. We can't create 100 universes and see how many have cold spots. We have one data point, the universe we live in. 2% isn't impossible. It's just, you could buy a lottery ticket with better odds. At least the cold spot is an ancient trace, frozen in the CMB from when the universe was young. But what about something happening right now? Giant radio circles. Perfect circles. Hundreds of thousands of light years across. We just discovered them, and we have no idea what they are. 2019, the ASCAP telescope in Australia caught something that had never been seen before. Perfect radio circles. Hundreds of thousands of light years across, visible only in radio wavelengths. They called them odd radio circles, ORCs. Let me tell you about one of the most recent mysteries in astronomy. These things were discovered just a few years ago, and we still don't know what they are. The discovery happened when a team led by astronomer Ray Norris was using the Australian Square Kilometre Array Pathfinder, or ASCAP for short. It's a radio telescope designed to survey large areas of the sky. Radio telescopes see the universe differently than optical telescopes. They detect radio waves instead of visible light. When the team processed their data, they found circular structures, perfect circles. At first, they thought it was a processing error. Circles are suspicious in astronomy. Nature rarely makes perfect circles. So when you see one in your data, your first instinct is to assume something went wrong. But when they checked the data carefully, the circles were real. They weren't artifacts. They weren't glitches. They were actual structures out there in space. The team found 3 initially. Then they found more. Other telescopes confirmed them. As of 2025, we found about a dozen ORCs. Let me describe what we're seeing. Each ORC is a ring or shell of radio emission. The ring is nearly circular, sometimes perfectly so. At the center, there's usually an elliptical galaxy. The galaxy appears normal at optical wavelengths. Nothing obvious about it would explain the radio ring around it. The rings are enormous. Some are more than 1 million light years across. That's 10 times the diameter of the Milky Way. These are huge structures. We're not talking about small objects here. Now, astronomers see circular things in the sky sometimes. Supernova remnants can look circular. They're the expanding shells of debris from exploded stars. But supernova remnants are much smaller, typically a few light years to a few dozen light years across. Orcses are hundreds of thousands of light years wide. They're not supernova remnants. Planetary nebulae can also look circular. These are shells of gas shed by dying stars. Beautiful structures, but again, they're much smaller, a few light years at most. And they're in our galaxy. Orcses are definitely not planetary nebulae. Some galaxies have radio lobes, where jets from a central black hole shoot matter out into space. These can create circular structures when viewed from certain angles. But ORCs don't match the characteristics of radio galaxies. The central galaxies don't show the active supermassive black holes that would be needed to create such structures. So what are they? Honestly, we don't know. Scientists have proposed several theories. Maybe they're shock waves from massive explosions in the centers of galaxies. If a galaxy went through a period of intense star formation, or if its central black hole suddenly became active, it could create a blast wave that expands outward. Over millions of years, this wave could create a spherical shell of radio emission. But if that's the case, why don't we see more of them? Galaxies go through active phases all the time. We should see these structures more often if they're caused by common galactic events. Another theory suggests they might be related to merging galaxies. When two galaxies collide, all sorts of crazy things happen. Shock waves ripple through the gas. Stars are flung around. Maybe the collision creates shock waves that expand outward as spherical shells. But again, galaxy mergers are common. Orcses are rare. If mergers created Orcses, we'd expect to see far more of them than we do. Some scientists have suggested even more exotic explanations. Maybe they're the imprints of primordial events from the early universe. Maybe they're related to cosmic strings or some other esoteric feature of space-time. These ideas are pretty speculative. We're grasping at straws, trying to explain what we're seeing. The truth is, we're still in the discovery phase with ORCs. We've only known about them for a few years. We need more observations. We need to find more of them. We need to study the galaxies at their centers in more detail. We need to understand what makes these galaxies special. What makes ORCs particularly fascinating is that they represent something genuinely new. We've been studying the radio sky for decades. We've built radio telescopes. We've mapped the universe in radio wavelengths. But ORCs only showed up when we built more sensitive instruments. They were always there. We just couldn't see them until recently. This tells you something important about astronomy. The universe is full of things we haven't discovered yet, not because they're hiding, but because we don't have the tools to see them. Every time we build a better telescope or observe in a new wavelength, we find something unexpected. Orcses are a perfect example. Nobody predicted them. Nobody was looking for giant radio circles around galaxies. They were a complete surprise. And now, astronomers are trying to figure out what they are and what they tell us about the universe. It's exciting because it's genuinely mysterious. We don't have a good explanation yet. Several possibilities are being explored, but none fits perfectly. As technology improves, we'll find more ORCs. Each new discovery will give us more data. we'll start to see patterns. We'll understand what conditions create them. Eventually, we'll solve the mystery. But right now in 2025, they remain unexplained. These strange structures in the radio sky are waiting for someone to figure them out. It's like turning on night vision for the first time and discovering there are things moving around your house that you never knew existed. They were always there. You just couldn't see them. So that's it. The things too big to believe. Giant structures that break the rules. Enormous voids that shouldn't be so empty. Cold spots that shouldn't be so cold. And perfect radio circles that shouldn't exist at all. But what about things that are too strange to explain? Let's zoom back in from structures billions of light years across to a single star. This star contains radioactive elements, elements that should have decayed away billions of years ago, but they're still there. HD 101065. It's 370 light years away. Looks normal, but inside it are technetium and promethium, half-life a few million years. The star billions of years old. The math doesn't work. Let me tell you about a star that breaks the rules of nuclear physics, or at least seems to. Przybylski's star sits in the constellation Centaurus. From a distance, it looks ordinary. It's an A-type star, about twice as massive as the Sun, and roughly 6 times more luminous. Nothing unusual there. Plenty of stars like that in the sky. But when astronomers analyzed its light spectrum, they found something absolutely bizarre. The star contains elements that shouldn't exist in any star for more than a few weeks or months. Here's why this is a problem. Stars create elements through nuclear fusion. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. In the most massive stars, the process continues creating heavier elements up to iron. Elements heavier than iron are created in supernova explosions and other energetic events. When a massive star explodes, the incredible pressures and temperatures create these heavy elements. They're scattered into space, where they can be incorporated into new stars. So when we see heavy elements in a star's atmosphere, we assume they were there when the star formed. The star was born from a cloud of gas that contained material from previous generations of stars, including their heavy elements. But here's the catch. Some heavy elements are radioactive. They decay over time. Uranium, for example, has a half-life of about 4.5 billion years. That means half of any uranium will decay into lighter elements in 4.5 billion years. But even after billions of years, some uranium is still around. Technetium is different. Technetium has no stable isotopes. All forms of technetium are radioactive. The longest-lived isotope, technetium-98, has a half-life of about 4.2 million years. That's nothing on cosmic timescales. Przybylski's star is probably several billion years old. Based on its characteristics, it's a mature star, not a young one. If it formed with technetium in its atmosphere, that technetium would have decayed away billions of years ago. There should be none left. Yet when astronomers observe the star's spectrum, they see clear evidence of technetium. They also see promethium, another radioactive element with a short half-life. And they've seen these elements consistently since the star was first studied in detail in the 1960s. For more than 60 years, this star has been showing us elements that shouldn't be there. So, where is this technetium coming from? There are a few possibilities, none of them completely satisfying. One idea is that the star is creating technetium on its surface through some unknown nuclear process. Maybe there's a mechanism we don't understand that can produce these elements in the star's atmosphere, but this seems unlikely. We have a pretty good understanding of nuclear physics. There's no known process that could do this in the cool outer layers of a star. The temperatures and pressures aren't high enough. Another idea is that technetium is being brought up from the star's interior. Maybe deep inside, the star nuclear reactions are creating technetium, and convection currents are carrying it to the surface. But this doesn't quite work either. The star's interior isn't hot enough to create technetium through normal nuclear reactions. The processes that create such elements typically require supernova conditions. A third idea, which sounds like science fiction, is that the star contains super heavy elements with atomic numbers far beyond anything we've seen. In theoretical nuclear physics, there's something called the island of stability. The idea is that if you go far enough up the periodic table, beyond the known elements, you might find a region where certain super heavy elements are relatively stable. Some of these super heavy elements, if they exist, might decay into technetium or promethium as intermediate products. So, the star might contain super heavy elements that are slowly decaying, replenishing the supply of technetium and promethium. This is highly speculative. We've never observed super heavy elements in nature. We've created a few in particle accelerators, but they decay almost instantly. The island of stability is a theoretical prediction, not an established fact. But Przybylski's star is so weird that astronomers are willing to consider exotic explanations. If the star really does contain super heavy elements, it would be evidence of matter we've never encountered in nature before. Another strange thing about the star is its composition. It has unusually high amounts of certain rare Earth elements. Its spectrum shows strong lines of elements like holmium dysprosium and europium. These elements are much more abundant in Przybylski's star than in the Sun. It's what's called a chemically peculiar star. There are several types of chemically peculiar stars, and they're thought to arise because of atmospheric processes that concentrate certain elements. Radiation pressure and magnetic fields can cause some elements to sink or float in the star's atmosphere, creating unusual abundances. But even among chemically peculiar stars, Przybylski's star is exceptional. Its abundance patterns are more extreme than almost any other star, and the presence of short-lived radioactive elements is unique. Some astronomers have wondered if Przybylski's star might have a companion. Maybe it's in a binary system with a neutron star or white dwarf, and material from the companion is falling onto Przybylski's star, bringing radioactive elements with it. But we see no evidence of a companion. The star's motion doesn't show the wobble we'd expect from an orbiting partner. It appears to be alone. As of 2025, Przybylski's star remains a mystery. For more than 60 years, astronomers have been observing it. And for more than 60 years, it's shown technetium and promethium in its spectrum. These elements should have decayed away long ago, yet they're still there. It's like finding milk in your refrigerator with an expiration date 1 billion years ago, but it's still fresh. You'd be concerned. And that's 10 mysteries tonight. From a 72-second signal to structures 3 billion light years across. from a star older than time to unexplained radio circles. But remember this, these 10 mysteries seem unrelated at first glance. An interstellar object passing through, a radio signal from the 1970s, a blinking star, an impossible explosion, a star older than the universe, giant structures, empty voids, a cold spot, perfect radio circles, star with elements that shouldn't exist. What do they have in common? Maybe nothing. Maybe each has its own separate explanation. But maybe they're all pieces of a larger puzzle. Let me tell you how science progresses. Often, it starts with anomalies, observations that don't fit, little mysteries scattered across different fields. At first, they seem unconnected. Each one is just a problem to solve. Then someone comes along and sees the pattern. They realize these separate anomalies are all symptoms of the same underlying truth. They connect the dots, and suddenly, everything makes sense. That's how relativity happened. In the late 1800s, there were several problems in physics. The orbit of Mercury didn't quite match predictions. It was precessing slightly more than Newton's laws predicted. Nobody could explain it. The speed of light seemed to be constant, regardless of how you measured it. That made no sense. If you're moving toward a light source, you should measure the light as traveling faster. But experiments showed light always traveled at the same speed. Always, no matter what. These seemed like separate issues. The Mercury orbit problem, the light speed problem, different phenomena, different observations. Then Einstein came along and showed they were both explained by the same new theory. Relativity connected the dots. Space and time aren't separate, they're woven together. Mass warps space-time, and suddenly both problems made sense. The same thing happened with dark energy. In the 1990s, astronomers were measuring distant supernovae to determine how fast the universe's expansion was slowing down. Gravity from all the matter should be pulling everything back together, decelerating the expansion. But they found the opposite. The expansion was accelerating, getting faster. That made no sense. What could be pushing the universe apart? This observation didn't fit. It was an anomaly, a mystery. But instead of ignoring it, astronomers followed where the evidence led. They proposed dark energy, a mysterious force that makes up about 68% of the universe's total energy. We still don't really know what dark energy is, but we know it exists because the observations demand it. So maybe that's what's happening now with these mysteries. Maybe they're telling us something fundamental about the universe that we haven't grasped yet. Maybe there's a connection we're not seeing. Think about it. Oumuamua behaves like it's being pushed by something we can't explain. The WOW signal used a frequency that suggests intelligence. Tabby's star dims in ways no natural process should produce. F-bots release energy faster and brighter than theory allows. The Methuselah star is older than time. The giant arc and big ring are larger than structure should grow. The Boötes void is emptier than it should be. The CMB cold spot is colder than probability allows. ORCs form perfect circles we can't explain. Przybylski's star contains elements that can't exist. Each one breaks the rules in a different way, but they all break the rules. Maybe that's the pattern. Maybe the universe is more complex than our current models suggest. Maybe there are processes, phenomena, or physics we don't fully understand yet. Or maybe not. Maybe each mystery has its own mundane explanation. Maybe the WOW signal was a comet. Maybe Tabby's star has a dust cloud. Maybe Orse's are shock waves. Maybe the giant arc is just chance. Maybe Przybylski's star has some unknown nuclear process. We won't know until we figure them out, but the possibility that they're connected, that they're all pointing towards something bigger, that's exciting. That's what makes this such a fascinating time to study astronomy, like puzzle pieces. Individually, they're just odd shapes. They don't make sense alone. But when you arrange them correctly, when you see how they fit together, suddenly a picture emerges. Something you couldn't see before. We might be looking at the pieces right now, scattered across astronomy, waiting for someone to see the pattern, to realize how they connect, to propose the new theory that explains them all. Or we might be looking at 10 separate puzzles, 10 unrelated mysteries, each needing its own solution. We don't know yet, but here's what we do know. Every major breakthrough in physics started with observations that didn't fit, with anomalies that couldn't be explained, with mysteries that challenged the existing models. Quantum mechanics emerged because atoms behaved strangely. Relativity emerged because light and gravity didn't follow Newton's rules. Dark matter was discovered because galaxies rotated wrong. Dark energy was discovered because the universe expanded wrong. These mysteries forced scientists to think differently, to question their assumptions, to develop new theories, and each time our understanding of the universe expanded. That's what mysteries do. They're not obstacles, they're opportunities. Opportunities to learn something new, to discover something fundamental, to push the boundaries of knowledge. So whether these 10 mysteries are connected or not, they're valuable. They're showing us the edges of our understanding, the places where our theories break down, the phenomena we can't yet explain. And somewhere in studying them, we'll learn something. Maybe something small, maybe something revolutionary, but we'll learn. That's the nature of science. Technology drives this process forward. Better tools reveal new mysteries, and those mysteries drive us to build even better tools. It's a cycle, a feedback loop of discovery and innovation. Here's something you need to understand about astronomy. Every major mystery I've told you about tonight was discovered with a specific piece of technology, and we only found them because we built new instruments. The WOW Signal Big Ear radio telescope. It was one of the first telescopes specifically designed to search for alien signals. Before Big Ear, we weren't listening in the right way. We weren't looking. Oumuamua Pan-STARRS telescope in Hawaii. It had only been operational for 7 months when it detected that interstellar visitor. Before Pan-STARRS, we wouldn't have seen it. Tabby's star Kepler space telescope. Kepler monitored 150,000 stars continuously for years. Before Kepler, we couldn't do that kind of sustained observation. We would never have caught those strange dimmings. AT2018 Cow and the FBOTs, a network of automated survey telescopes that scan the sky every night. These surveys find hundreds of transients. Most are normal, but occasionally they catch something that breaks the rules. ORC's ASCAP radio telescope in Australia, brand new technology, more sensitive, surveys larger areas faster. Before ASCAP ORCs were invisible. You see the pattern. New technology equals new discoveries. Every time we build a better telescope, we find surprises. Every single time. This isn't coincidence. It's fundamental to how discovery works. The universe is full of phenomena we can't detect yet, not because they're hiding, because we lack the tools to see them. Think about radio astronomy. Before the 1930s, we had no idea the universe was full of radio sources. We couldn't see them. Then we built radio telescopes and discovered a whole new universe. Pulsars, quasars, the cosmic microwave background, radio galaxies, all invisible to optical telescopes. X-ray astronomy began in the 1960s. Suddenly, we could see hot gas black holes, accreting matter, supernova remnants, glowing in X-rays. An entire universe that optical telescopes missed. Infrared astronomy, gamma ray astronomy, gravitational wave astronomy. Each new wavelength, each new detection method revealed phenomena we hadn't imagined. And it's not slowing down. We're building even better instruments right now. The extremely large telescope is under construction in Chile. When complete, it will have a mirror 39 meters across. That's enormous. It will be able to see incredibly faint and distant objects. It will be able to analyze the atmospheres of exoplanets, looking for signs of life. The square kilometer array is being built across South Africa and Australia. When finished, it will have a collecting area of 1 square kilometer. That's about 250 acres of radio receivers. It will be 50 times more sensitive than any current radio telescope. If there are radio signals out there, like the WOW signal, the square kilometer array will find them. If there are more orxies, it will see them. It will revolutionize radio astronomy. The James Webb Space Telescope is already operating. It's observing in infrared, seeing through dust clouds, looking at the earliest galaxies, studying exoplanet atmospheres. It's finding things we didn't expect. Already, NASA is planning new space telescopes. Some will look for signs of life on exoplanets. Some will study the early universe. Some will map dark matter. Each will have the potential to discover something unexpected. Here's what history teaches us. Every time we build a better telescope, we find surprises. Every single time. There has never been a case where we built a more sensitive instrument and found exactly what we expected, and nothing more. The universe always surprises us, so we can be pretty confident that in the coming decades, we'll discover more strange things, more mysteries to puzzle over, more observations that don't fit our theories. In the next 10 years, I guarantee we'll find at least 10 new mysteries we can't even imagine right now. Phenomena we haven't thought of. Objects we didn't know could exist. Processes that will force us to rethink our models. That's not pessimism. That's confidence based on history. The universe is stranger than we know. It's probably stranger than we can know, given our current level of technology and understanding. But we keep building better tools. We keep looking deeper. We keep pushing the boundaries. And every time we do, the universe reveals something new. The mysteries I've told you about tonight, they're just the beginning. They're the mysteries we've found so far with the technology we have now. Imagine what we'll find with the technology we'll have in 10 years, 20 years, 50 years. The frontier of knowledge keeps expanding. The more we learn, the more we realize how much we don't know. Each answer raises new questions. Each discovery reveals new mysteries. And that's exactly how it should be. That's the nature of science. An endless journey into the unknown. Always discovering. Always surprised. Always learning. The tools drive discovery. The discoveries drive us to build better tools. It's a beautiful cycle, and we're living in the middle of it right now. Let me tell you what science really is, because I think a lot of people misunderstand it. Science isn't about having all the answers. It's not about being certain. It's not about never being wrong. Science is about being honest about what we don't know. The wow signal happened in 1977. That's almost 50 years ago. And you know what? We still don't know what it was. Scientists have been honest about that for 5 decades. They've proposed various possibilities: natural radio sources, alien signals, terrestrial interference. But they admit none of these explanations is completely satisfying. That honesty is valuable. It means when we finally do figure out what the wow signal was, we'll know the explanation is based on solid evidence, not wishful thinking, not convenient assumptions, not ignoring inconvenient data. The same is true for all these mysteries. Scientists are being honest about what they don't understand. That honesty is a strength, not a weakness. This is very different from other ways of knowing. In some belief systems, admitting you don't know something is seen as weakness. There's pressure to have answers, even if those answers aren't well supported. There's resistance to changing your mind even when evidence suggests you should. Science takes the opposite approach. Admitting you don't know is honest. It's the first step toward knowing. You can't solve a problem if you pretend it doesn't exist, or if you accept a convenient answer without evidence. Science is also self-correcting. When we make a mistake, when a theory turns out to be wrong, we change it. We update our understanding based on new evidence. History is full of examples. Scientists used to think Earth was the center of the universe. Observations proved otherwise. We changed our minds. Scientists used to think the universe was static and unchanging. Observation showed it was expanding. We changed our minds. Scientists used to think nothing could escape a black hole. Theoretical work by Stephen Hawking showed that black holes can evaporate through quantum processes. We changed our minds. Each time the scientific community updated its views based on evidence. That's how it should work. Our understanding should evolve as we learn more. The mysteries I've described will likely lead to changes in our understanding. Maybe small changes, maybe large ones. But whatever we learn from them will make our picture of the universe more accurate. That's the goal. Not to protect cherished theories, not to cling to ideas because they're comfortable or familiar, but to understand reality as it actually is, even when reality is strange, even when it contradicts our expectations. There's another important aspect of science: living with uncertainty, being comfortable not having all the answers yet. In our daily lives, we're used to getting answers quickly. If we don't know something, we can look it up online in seconds. We're used to immediate information, but the universe doesn't work that way. Some questions take decades to answer. Some take centuries. Some might never be answered, at least not in our lifetimes. The wow signal has been unanswered for almost 50 years. Tabby's star has been puzzling us for over a decade. These aren't easy problems. They require patience, persistence, willingness to live with not knowing. That's hard. It's much more comfortable to have answers than questions. But the universe is under no obligation to make sense to us on our schedule. We have to be patient. We have to keep observing, keep thinking, keep trying. And while we wait for answers, we learn other things. We develop new technologies. We train new generations of scientists. We make observations that might not answer the original question, but reveal something else. Interesting. In science, I don't know is the bravest answer. It's honest, it's humble, it acknowledges the limits of current knowledge. On Facebook, saying I don't know is apparently why you write a 5,000-word comment explaining why you're definitely right anyway. The mysteries are valuable precisely because we don't understand them. They're showing us the edges of knowledge, the places where our theories need work, the phenomena we need to study more carefully. They're invitations to explore, to discover, to learn. Each mystery is the universe's way of saying, you don't know everything yet, and that's a good thing. Here's something we're not good at anymore: waiting for answers, not knowing, living with uncertainty. We live in the age of Google, of instant information. You have a question, you type it into your phone. 3 seconds later, you have an answer. We're conditioned to expect immediate knowledge, immediate resolution, immediate certainty. But the universe doesn't work that way. Some questions take decades to answer. Some take centuries. Some might never be answered, at least not in our lifetimes. And that's hard for us to accept. The wow signal happened in 1977, almost 50 years ago. We still don't know what it was. That's a long time to wait for an answer. A long time to live with not knowing. Tabby's star has been puzzling us since 2011. That's over a decade of observations, thousands of hours of telescope time, hundreds of scientific papers, and we still don't have a definitive explanation. We have theories, we have possibilities, but we don't have certainty. Oumuamua passed through our solar system in 2017. We had 11 days to study it. Then it was gone. Forever. We'll never get another chance to observe it up close. We'll never know for sure if it was natural or artificial. That uncertainty is permanent. This bothers us deeply because humans are pattern-seeking creatures. It's hardwired into our brains. We want explanations. We need to understand. We feel uncomfortable with mysteries. Our ancestors saw patterns in the stars and invented constellations. They saw the sun rise and set and invented stories about gods pulling it across the sky. They didn't understand what they were seeing, so they created explanations. Even wrong explanations felt better than no explanations. We still do this. We still want answers, even when the honest answer is, we don't know yet. But here's what mysteries do for us. They keep us humble. They remind us that we don't have everything figured out, that our understanding is incomplete, that we might be wrong about important things. Throughout history, humans have been confidently wrong about major questions. We thought Earth was flat. We thought it was the center of the universe. We thought continents didn't move. We thought atoms were the smallest things. We thought the universe was static and unchanging. We were wrong about all of these. Completely wrong. And we were confident about our wrongness. We built entire worldviews around these incorrect ideas. So what are we confidently wrong about today? What fundamental assumptions are we making that future generations will look back on and shake their heads? Maybe something about dark matter, maybe something about dark energy, maybe something about the nature of time or space or consciousness. We don't know what we don't know. That's the whole point. The mysteries remind us of this. They're humbling. They show us the edges of our knowledge. the places where our theories break down, the phenomena we can't explain yet, and that's valuable. That humility is important. It keeps us honest, it keeps us questioning, it prevents us from becoming too certain, too rigid, too closed to new ideas. Think about how short our time observing the universe has been. Modern astronomy really began with Galileo pointing his telescope at the sky in 1609. That's about 400 years of serious astronomical observation. The universe is 13.8 billion years old. Do the math. 400 years is zero. 0.003% of the universe's age. We've been looking at the cosmos for the tiniest fraction of its existence. We just opened our eyes. We're infants in cosmic terms. And during this tiny fraction of time, we've discovered an enormous amount. We've figured out what stars are, how they work, how they're born and die. We've discovered other galaxies. We've learned the universe is expanding. We've detected gravitational waves. We've found black holes, neutron stars, exoplanets. We've mapped the cosmic web. We've observed the cosmic microwave background. All of this in just 400 years. Imagine what we'll discover in the next 400 years, or the next 4,000 years, or the next 4 million. The universe is full of secrets. Some we've uncovered, many more remain hidden. Every telescope we build reveals new mysteries. Every new wavelength we observe shows us structures we didn't know existed. Radio astronomy began in the 1930s. Before that, we had no idea the universe was full of radio sources. We couldn't see pulsars, quasars, or the cosmic microwave background. We didn't know about ORCs because we couldn't detect them. X-ray astronomy began in the 1960s. Infrared astronomy, gamma-ray astronomy, gravitational wave astronomy. Each opened a new window on the universe. Each revealed phenomena we hadn't imagined. What will we discover with the next generation of telescopes? What wavelengths haven't we observed yet? What techniques haven't we developed? What phenomena are out there right now, waiting to be discovered that we can't even conceive of? I guarantee that in 50 years, we'll know about things that sound like science fiction today. We'll have detected phenomena we currently can't imagine. We'll understand processes we haven't thought of. The universe is stranger than we know. It's probably stranger than we can know given our current limitations. But here's the beautiful thing. We keep trying. We keep building better instruments. We keep asking questions. We keep pushing the boundaries of knowledge. And every time we do, we learn something new. Sometimes the answer raises more questions. Sometimes solving one mystery reveals 10 more. That's not frustrating. That's exciting. It means the journey continues. There's always more to discover, always something new to learn. The mysteries I've told you about tonight aren't problems to be frustrated by. They're invitations. Invitations to keep looking, keep questioning, keep exploring. They're the universe's way of saying, you don't understand everything yet. Keep trying, and we will, because that's what we do. We're curious. We're explorers. We're pattern seekers who want to understand our place in the cosmos. The wow signal will probably remain mysterious for our lifetimes, maybe forever. But the search for it has advanced radio astronomy. It's developed better methods for analyzing signals. It's taught us to think carefully about what evidence for extraterrestrial intelligence would look like. Tabby's star has taught us that stars are more complex than we thought. that there are behaviors we didn't anticipate, that we need better models of how dust behaves around stars. Even if we never definitively explain its dimming, we've learned valuable things in the attempt. The same is true for all these mysteries. Even if we don't solve them, the process of trying teaches us things, develops new methods, reveals unexpected phenomena, pushes us to think harder and deeper about how the universe works. That's the value of uncertainty. It drives us forward. It motivates us to build better tools, to think more creatively, to question our assumptions, to explore further. Living with uncertainty isn't weakness. It's honest. It's humble. It's the foundation of all real progress. Because you can't learn if you think you already know everything. The universe is teaching us this lesson over and over, and it's a lesson worth learning. So there you have it. 10 of the strangest things we've found in space. They're real. They're measurable. We've observed them with multiple instruments. We have data. We have evidence. But we don't understand them. An object from outside our solar system that accelerated in ways gravity can't explain. A radio signal that lasted 72 seconds and used the frequency intelligent civilizations would choose. A star that loses 22% of its brightness for no apparent reason. An explosion 100 times brighter than supernovae and faster than anything should be. A star that appears older than the universe itself. Structures spanning billions of light years. That theory says can't exist. A void containing 60 galaxies where 2,000 should be. A cold spot in the cosmic microwave background with only a 2% chance of existing. Perfect radio circles, hundreds of thousands of light years across. A star containing radioactive elements that should have decayed away billions of years ago. 10 mysteries. 10 things that break the rules. 10 observations that don't fit our current understanding. But here's what I want you to understand. These aren't problems. These are invitations. Each mystery is the universe inviting us to explore, to discover, to think differently, to question our assumptions, to push the boundaries of knowledge. The wow signal is inviting us to keep listening, to build better radio telescopes, to think carefully about what signals from other civilizations might look like, to consider our place in a potentially inhabited universe. Oumuamua is inviting us to watch for more interstellar visitors, to be ready when the next one comes, to think about what natural or artificial objects might drift between the stars. Tabby's star is inviting us to study stellar behavior more carefully, to understand that stars can do things we haven't seen before, to develop better models of how dust and debris interact with starlight. The giant arc and big ring are inviting us to reconsider how structure formed in the universe, to question whether the cosmological principle holds at the largest scales, to think about whether our models of cosmic evolution are complete. Each mystery is the universe saying, "You don't know everything yet. There's more to discover. Keep looking." And we will. Because that's what we do. We're explorers. We're curious. We want to understand. In our lifetimes, we'll see breakthroughs. Some of these mysteries will be solved. We'll finally understand what caused them, what processes created them, why they exist. And when we solve them, we'll learn something fundamental about how the universe works. Maybe we'll discover new physics. Maybe we'll find evidence of life elsewhere. Maybe we'll understand dark matter or dark energy better. Maybe we'll learn something we can't even anticipate yet. But solving these mysteries will also create new ones. That's how science works. Every answer raises new questions. Every discovery reveals new mysteries. The frontier keeps expanding. There's always more to explore. And that's beautiful. That's exciting. That means the journey never ends. There's always something new to discover. Always something we don't understand yet. Always another mystery waiting. Tonight, when you look up at the sky, remember this. Every photon that hits your eye has traveled through space, some for thousands of years, some for millions, some for billions. That light left a distant star long ago. It crossed unimaginable distances through the vacuum of space, past countless other stars, through dust clouds and voids, and it ended its journey by entering your eye, by striking your retina, by being absorbed and converted into a signal your brain interprets as sight. You are connected to the cosmos. Those photons traveled all that way to reach you. You are seeing light from the past, light that began its journey before humans existed, before Earth formed, before the sun ignited. And you're not just connected to the universe, you are part of it. The atoms in your body were forged in stars. Carbon, oxygen, nitrogen, iron, all created by nuclear fusion in stellar cores, released when those stars exploded, scattered through space, eventually incorporated into the cloud that formed our solar system. That became Earth. That became you. You're made of star stuff. That's not poetry. That's literal truth. You are the universe looking at itself, conscious, aware, questioning. And that's incredible. So that's tonight's journey. From a 72-second signal to structures 3 billion light years across. From an interstellar intruder to a star older than time. From perfect radio circles to impossible explosions. From giant voids to cold spots in ancient light. 10 mysteries, 10 invitations, 10 reminders that the universe is stranger than we think and more beautiful than we can imagine. The universe is strange, wonderfully, beautifully strange. And that's not a problem. That's a promise. Somewhere out there right now, strange things are happening. Things we haven't detected yet. Things we can't imagine. Things that will puzzle us when we finally discover them. Things that will challenge everything we think we know. And one day, maybe in our lifetimes, maybe in our children's lifetimes, we'll discover something that changes everything. A signal that's clearly artificial. A phenomenon that requires new physics to explain. Evidence of life on another world. Something that forces us to completely rethink our place in the cosmos. That discovery is coming. It's out there waiting. And we're going to find it. Because we're lucky. We live in an age with the technology to explore the universe. With telescopes that can see across billions of light years. With instruments that can detect the faintest whispers from space. With computers that can analyze vast amounts of data. We're living at exactly the right time to make these discoveries, to solve these mysteries, to push human knowledge further than it's ever gone before. So sleep well tonight. And when you look up at the stars, remember that the universe is full of mysteries. Some we know about, most we don't. And every one of them is an invitation to explore, to discover, to understand. The star you see tonight might be doing something nobody understands. It might be blinking like Tabby's star. It might contain elements that shouldn't exist like Przybylski's star. It might be older than it should be like the Methuselah star. And that's the most wonderful thing about the universe. It's strange, it's mysterious, it's full of surprises, and we get to explore it